Alrighty, that's 5:30. Well, let's make a start. So I did mention last week that Class 2 might start being for probability, but I realised a decent number of you have your SAC like literally this week. I know Taihan has it literally tomorrow. So makes a decent amount of sense to just finish off the last bit of integration, and then maybe in the Friday class we'll have a look at the probability stuff for the first time. Assuming, of course, there's nothing within the last two classes that we'd like to review for that. But okay, let's crack on then. So last we did this question 12. I kind of did an overview of what you would do in these questions here. Since we've been doing such a focus on these kinds of questions, we could probably go through these at a bit of a faster pace, and maybe in doing so, if there are things you need me to clarify further, let me know and I'll go back. But for a lot of us, this should now be at a stage where these are quite easy questions. So let's try and give that a shot. And again, if I go too fast, feel free to let me know and I'll walk it back. First, let's get some background information. Okay, so we've got a water cooling device. For the first 30 minutes operation, the circulation follows the following sequence. Water flows in for first 3 minutes, then another 3 minutes water flows out, in, out for a total duration of 30 minutes. The rate of flow of water is given by this function. So although it's got the sort of f of x notation, this is effectively a derivative, right? It's the rate of flow over time, not the actual number of liters, it's the number of liters per minute. So we'll treat it like as if it was a derivative equation. Initially there are 4 liters of water in the device, so that is to say at t equals 0, we're not saying that r is 4. R would be the rate, which you might assume to be 0. It would have to be calculated here. But if we do like a quick look, putting 0 there turns that to 1. It's now 10 sine of 0, 0, 0. So yeah, the rate would be 0. Further reinforcing this is a rate equation, not a quantity equation. But okay, first couple of questions, find r of 0, r of 3. There's nothing worth talking about there. Just shove in 0, shove in 3. Calculator. Find derivative. Again, nothing crazy worth talking about at all. Kaz will instantly achieve that, and if you had to do a tech-free, you would do a product rule, because it's a product of the exponential and the circular function. Solve for r dash equals 0. Again, this is just Kaz quickly, so let's do that. Maybe 3, 1. Function derivative is equal to 0, making sure we put the domain that the question has told us to do. So we're doing 0 to 12 in this case, so let's do exactly that. 0 less than equal to x less than equal to 12. That's going to get us some weird looking exact values, which we will end up using. One of the things you can do is you can like pull a copy of it down to try and see all of them there, and maybe even control enter just so it's easier to read like how many do you actually have, because it's a bit easier to read the decimals than it is for the exact, but you do still want the exacts here. This question was probably worded a bit poorly because writing all those out in exact form is unpleasant and having that as part of your SAC would be less than ideal because of all the time you'd be spending writing. So normally it would be something that you'd have like to a number of decimal places. Anyway, next up, part I, find the coordinates of the stationary points for the function r of t. So the stationary points of r of t, which is why the whole derivative equals 0 was done in the first place. Well, partly because the question just told us to, but that's what it's leading into. Anytime you set derivative equal to 0, you find the stationary points of the original function, or at least more specifically the x coordinates of it. So all you would do is take each of these individual exact values, Control C, Control V into the original function, because you want to convert that to a corresponding y value, which again has a nasty response for it. This one, yet again, did not say number of decimal points, but looking at the answers, they did intend to have a number of decimal places here. So you'd be looking at the coordinate 8.6-ish, and if I rip this one off, that would correspond with x equals 1.4-ish or so. Okay, solve the equation r of t equals 0. Okay, same thing as solving the derivative equals 0, but we're just not going to put the derivative. I don't think it's worth even doing that. Sketch the graph, sure, why not? So we got our function, setting our domain. So we were told it was from 0 to 12, so we'll do exactly that. And we'll fix up our y-axis a little bit. It's, maybe 15 to 15. Cool. This kind of shape, can anyone tell me why it does this? If you have a look at the function definition itself, in the actual textbook, you got an exponential multiplying a sine graph. Can anyone, based off of that function, explain why we're getting this sort of behavior?
Negative fractional decimal.
Yeah, exactly. You have that negative exponent in the exponential, which has this basic decaying exponential. As x increases, the y value decreases close to 0 asymptotically. It's being multiplied by 10, so it's being magnified, so it does that at a slightly slower rate. And the circular function portion is why we're getting the circular function behavior. Cool. Hey Chris, joined a little bit late. What part are we up to right now? We are up to just part E, sketching the graph. A lot of these were quite quick and easy, just sub in values, find derivative, set derivative equals 0. Nothing crazy has been done so far. This is where the questions do get interesting and worth actually discussing. So I'll get you guys to have a think about this. So remember R of t being a rate equation. Part Fi. How many litres of water flowed into the device from t equals 0 to t equals 3? I won't speed through this one. I'll let you guys have a think about it and how we might approach it. Part F is asking for a number of litres, whereas our R of t equation is basically a derivative, it's a rate of flow. So it's not just going to be a matter of necessarily subbing in those values and finding the difference. It's a little bit more to it than that. Think about how you might go from rates of change to physical quantities. If you start with a rate of change equation, how do you then convert that equation into the physical quantity itself? Or in other words, going from a derivative to an original function, dy dx going back to y. What's the procedure via which we do that?
Anti-differentiate.
Anti-differentiate is correct. Nice. So, because we're talking about the actual physical quantity, how many litres, not the rate at which litre was flowing, not the rate at which liquid was flowing, we're going to anti-diff this back into the physical quantity itself. Now, it does specify 0 to 3 here. Can you elaborate further on what the next step might be after anti-diffing, or perhaps even getting it all done in one go? Because anti-diffing is definitely part of it. What's the significance of the 0 to 3? Okay, no worries. So the significance of the 0 to 3 you can interpret in a couple of different ways. One is that you just say, cool, I know that I got an antidiff to get back to the physical quantity itself, and now I want to find how many liters flowed into the device from 0 to 3. I now just want to say, okay, how many was there at t equals 0, how many was there at t equals 3, whatever the difference is was how much net flowed back in. So if we figure out h of 3, it's going to be 0. If we do h of 0, it's going to be... Whoops, never mind, that's the wrong equation. I should be using the new one that I defined. Number 3, and, well, let's control into that, and 0. Why does that still seem off? Yeah, okay, haven't completed the antidiff fully properly here. That's because we were told an initial value. Initially there are 4 liters of water in the device. So when you do your antidiff, it comes with this plus C term in there. And if you want to get a completed antidiff, then you need to include that initial value on there because you've got to solve for that plus C. Which is why just subbing in those values isn't going to quite cut it just now. So with that in mind, this definition of I of x needs a plus C in it, and we would then go and say I of 0 is equal to 4, solve for C, and then set that as our C value. Now we should get the proper behavior where if I shove in t equals 0 I get y equals 4, which is now consistent with the question itself. So when I then test my 0 to 3 and then find the difference between the two, I now get the actual amount that has flowed in. That's one way of doing it there. Any questions so far about that?
Sorry, I think I missed. What do we put in to get C?
To get C? Yeah, so to get C there, I was basically just saying I redefined the I of x, the antidiff function, to have a plus C involved in it, and then all I did was sub in a known point. That known point being the fact that initially there were 4 liters of water, or in other words, t equals 0 and y equals 4.
Okay.
Another question, got a bit distracted. Which part are we calculating? We were doing the part Fi, how many liters of water flowed into the device. One way of going about it, or the way that we've just discussed right now, is to get your antidiff, your proper full antidiff, with the plus C included as the actual value, and then finding the difference between the values. You know, what's I of 3, what's I of 0? That's going to get you your liters of water at t equals 3, liters of water at t equals 0. So the difference of which, if you subtract the two, whatever the difference between them is going to be how much flowed in, or out if it was a negative number. We all clear on that approach? Cool. The other approach, a slightly more sophisticated way of going about it, is to recognize that a definite integral is the same as what we just achieved. So if I control enter on that, we'll see that we have the exact same answer. The reason why is a bit more obvious when you think about what the steps of a definite integral are. Definite integral has 2 steps. First you do your antidiff. Second, you do capital F of top minus capital F of bottom. So in other words, once again, antidiff like we did before, shove in t equals 3, subtract from subbing in t equals 0. So it's the exact same steps outlined that we just did, except you're condensing that down into a single line of working. Is it clear enough why doing a definite integral works there? Awesome. That should then help you with part double I. How many liters of water flowed out of the device for t equals 3 to 6? What are we going to do there? Maybe before we answer that specifically, I'll touch on the fact that, technically speaking, solving for that plus C didn't matter. at least in the context of the fact that because it's a fixed value and you're finding a difference between two numbers, it's still just shifting where that difference is, not how big the difference is. The problem with not solving for the plus c is that you might later then use your equation incorrectly because you have this quantity equation that's got a wrong offset, it's got the wrong constant attached to it. And so if you have to answer any, like, at the end right here, how many liters of water are there at t equals 30, if you then shoved in t equals 30 into that, you get a number that was plus c off, whatever the plus c value was. But anyway, double I, it's worded the exact same, with the only difference being that it's from 3 to 6 instead of 0 to 3. So we'll literally grab the exact same set of working out and adjust the terminals accordingly. We get a negative number, hence that is the number of litres that have flowed out of the device rather than into. Part III, how many litres of water are in the device when t equals 6? And then they've even given you another reminder there. Remember, there are initially 4 litres of water. We've got a lot of tools at hand to now answer this. How might we go about it? Not only do we have a lot of tools available to us to answer it, but we have different ways we could answer this one actually. Okay, so again, it's a question asking the quantity, right? How much of a thing is in there at a specific time. So one of the more straightforward ways of doing this is just use our quantity equation. When we did our anti-diff, we labeled it I of x. Instead of putting in x, we're just going to put in t equals 6. The reminder was there just in case you didn't solve for your plus c. But we've already solved for our plus c, so this is now accounted for. So how many litres of water are there in the device? It's going to be the 8.26 there. Oops, I think I just accidentally closed that. There we go, that should be back to normal. Yeah, that's the most straightforward way of doing it. The other way that the book did, actually, was they used the last two answers, the part I, the part double I, to answer that, which they said, okay, cool. So if we know we're starting at 4, and 16.4 flowed into it, and then 12 flowed out of it, then 8.26 is what's left. Like, they just added the sequence of numbers until you got to your final answer at t equals 6. Because you'll notice that the domains of each of the previous questions lined up perfectly up until the end of t equals 6. More calculation than necessary by a lot. As long as you've done your anti-diff properly and solve for c, you can just shove it back in. Exact same thing for part G, right? How many litres of water are there at t equals 30? Like, the only difference between these sentences, well, the word there, but t equals 6 down to t equals 30. So we'll do exactly that, and we'll determine that there are approximately 13 litres there. Any questions about any of that sequence? Because question 13 is going to be something completely different. Cool. Okay, let's give it a shot then. So this is going to play with some trig identity stuff, which, funny enough, in uni I actually liked playing with these kinds of questions. This is the kind of thing that give you like first year engineering degree. You do a math course, and they like playing with these trig identities because they're strangely quite important. Well, not strangely, but they are quite important for like your signals and systems stuff. We're talking like propagation of information between digital systems. How hard is UniCalc compared to methods calc? It's basically like doing Spec in a semester, as opposed to across a full year. But given that you're also a year older and have already done a full methods course, so it's not as bad as the way I just made it sound. You do have a lot of the foundations to actually meet that demand. So yeah, not not as bad as I just made it sound. Yeah, at least in my degree that I did, electronics engineering, there were 2 math courses. One was like an intro to engineering math, and the other was... Actually, it was an elective, so you don't actually have to do that second one. That was just an elective because there was... At RMIT, I could not find too many that were of interest. One was a math course, the other was a physics course. Everything else just kind of seemed like a bit irrelevant. One of my friends did basket weaving as a as an elective, but that's another story. Okay, so what have we got going on here? Question 13. Oh, wanted to start commerce and have math units. Yeah, I don't... Oh, they do have math, they do have calc in commerce. Yeah, I mean, I guess you want to study your rates of change, and calculus is all about rates of change. I don't know how many, yeah, like maybe in commerce you'll be learning the digital way of calculating diff. It becomes very much like a sequence of rise over run equations where you have your data points on a spreadsheet and you calculate the little gradients between each of those data points. So it is calc in a certain way, but yeah, I can't imagine any continuous models that would work too well for commerce, because they'd all be approximations at the end of the day. Bell curves, we'll start looking at that in probability. That has a very funky looking equation that is widely used as a probability model for a lot of different things. So yeah, definitely applications in the real world for this sort of stuff. Okay, the hard part. So 13. Use the identities of that and that to show this equation is true. So one of the things I would be noticing here is both of these identities are cos 2x. So cos 2x is equal to something. Cos 2x is equal to something. So when I'm looking at my equations that I have here, I'm probably going to be starting out looking for that cos 2x, something that I can replace it with. Now, which one do you choose? This is kind of a guess and check, to be perfectly honest, which one's going to be relevant. You can be a bit more sophisticated with your choice here if you know what sec squared actually is by definition. Sec squared is 1 over cos squared. In fact, I wonder if the CAS will show that. 1 over cos x squared equals sec squared. Cool, okay. So just for everyone else, yeah, 1 over cos squared is sec squared. Yeah, Taha?
I just wanted to just have a go a little bit.
Oh yeah, brilliant.
I guess the first thing that probably comes to mind is what you were mentioning is they're both cos 2x for the identities.
Yeah.
So if you're subbing, you'd sub one of them into the numerator and the other one into the denominator. And probably the way I was thinking about it is that the first identity has -1 at the end. So you'd probably put that at the denominator because that's adding 1. So it'll cancel out nicely.
Yeah, yeah.
And then you put the other one maybe in the numerator.
Yeah, that would have them still...
I'm just guessing. Is that a good approach? Or
yeah, no, I like that actually. I like that. That's probably a good way of going about it, trying to cancel out those individual plus and minuses, ones. What I was sort of leading on towards was maybe, on knowing that sec squared is 1 over cos squared, maybe you do the cos squared thing on the bottom in that case. And that's just another way of saying the same thing, effectively. Because you still put the minus on with the plus 1 here, and you put the cos squared on the bottom, where you'd expect to be, given that we're looking to work towards sec squared. So 2 different lines of thinking, ending up with the same assumption, and these are assumptions. This might turn out to be shit. We have to change them around, but I guess we'll find out. So yeah, let's go ahead with that assumption. It's going to have 1 minus on the top, and we said we are going to do the second identity there, so replacing the cos 2x with 1 take 2 sine squared x. And then on the bottom, we're going to have 1 plus the identity on the left, which is going to be 2 cos squared take 1. 2 cos squared x take 1. From here, yep, some simplification. So 1 minus 1 cancels out.
Yeah, I think it's 2 sine squared x for the numerator and 2 cos squared x for the denominator.
2 sine squared x, 2 cos squared x. Yep, cool. Yes, that will be exactly what it is. Obviously the 2's will now cancel down. Now what's interesting is this one has sec squared minus 1. But we'll get there. Sine squared divided by cos squared. What is that? It's an identity that's not present here right now.
One.
Oh yeah, hang on, maybe it is. Well, it probably shouldn't be 1 exactly. You're thinking probably sine squared plus cos squared equals 1. Dividing them, let's see, if we divide both sides by cos squared.
Oh, that equals tan, doesn't it?
Yeah, that's what I was sort of looking for there, tan. So this will be tan squared. Cool. So we got tan squared there. Now we need to figure out how does tan squared go to sec squared take 1. Okay. There's something else we might be able to do. I think mentioning this is still pretty good. Knowing the relationship between sine squared and cos squared. Because maybe we don't want to convert this to tan. Unless you guys know a trig identity for tan, which they definitely exist. What does sine squared over cos squared give tan? It gives tan squared. So basically you can distribute, this is sine x squared, cos x squared. So if you imagine the square being distributed out, you now have sine over cos and then all of that squared. Sine over cos is tan, and then we just bring the square back in at the end. But yeah, maybe we don't want to do this. Maybe we want to leverage this here, this sine squared plus cos squared equals 1. And we know we want the cos portion in there because we want to get sec squared. Yeah, no, you're good. It's totally fine. This is a thing that I didn't fully appreciate in when I did methods either. The fact that sine divided by cos gives you tan. I just kind of like by rote memorize my tan values just without knowing they had any relationship with with this. Anyway, cool. So reconverting this, probably this sine squared into an equivalent cos squared makes sense to me. Because we want to keep cos squareds in there. So we'll go sine squared equals 1 minus cos squared. So replacing this sine squared with 1 minus cos squared, we'll see where that takes us. 1 minus cos squared x on cos squared. Yeah, okay, this is going to be it. Where might we take things from here to make it look more like the final answer that we need? With a reminder that 1 on cos squared gives us sec squared. So if we want to get a sec squared out of this, we want to somehow convert this into a 1 on cos squared. maybe we're freezing a bit. This is just splitting the fraction. So we have 1 over cos squared minus cos squared over cos squared. Just splitting the fraction there. 1 over cos squared x minus cos squared over cos squared, which is just 1. And then finally, that bit there is sec squared. And that's what we wanted. Yeah, Taihan?
Yeah, so I think I just don't have it, but I was wondering, isn't there an identity where it's tan squared x is equal to sec squared x minus 1?
Yeah, probably. That certainly would exist because it is. They do end up being equivalent. It's just not one that was on the methods list necessarily. You might have seen that elsewhere, or I don't know. Did you see it in methods?
I don't know, but
Yeah.
I'm just thinking because I feel like I've seen something like that before. I just checked
Yeah.
online.
Oh yeah, online there's a heap. There's really good stuff there. I brought down the ones that I thought were necessary for methods. Yeah, and totally. If you brought that one down here, you wouldn't need to drop what you were doing. If you got down to tan squared, you'd be able
I'll
to.
just try and finish trying it with that, and then I'll let you know how it goes.
Well, I mean that is the final answer. Tan
Oh,
squared
yeah.
goes to sec squared minus 1. So you got it. Yeah. So yeah, works 100%. There's a million different trig identities you can use to play with. In fact, we'll probably need another one because we now get to part B, hence evaluate. The approach here is straightforward enough. The thing on the inside is the same as the left-hand side of this equation, so rather than trying to antidiff this fraction, which is going to be quite challenging, we can antidiff the right-hand side instead. Now, I'm fairly certain sec squared doesn't show up on the formula sheet. Maybe I'm wrong about that. Let me pull that up.
It doesn't.
Yeah, it doesn't? Okay, cool. So, with that in mind, does tan show up on it? Antidiff of tan? Oh, wait, well, it shows up on the diff side, at the very least. Let me pull up... Where's it going to be? VCAR content. Okay, the formula sheet. So, yes, it cuts off pre-tan, but if we make use of our understanding of the fact that antidiff and diff are just basically going the opposite, right? We can make use of this and just reverse it effectively. So if we have a sec squared ax, antidiffing that should get us back to here. That's how it's always worked in that way. Haven't ever seen sec squared. Yeah, I mean that's fair. I've pretty much always removed the presence of sec in all of the stuff that I've been teaching because it is something you use more so in Spesh than anywhere else. But I guess what we're seeing here is that they do show it now and then in methods. So maybe that's a bit of a failing on my part for not introducing it or making it as clear that it's relevant. Especially because your CAS will sometimes give it to you as sec instead. But anyway, so making use of this, we can then infer that the antidiff of sec squared gets us back to tan, right? Antidiffing that. And so with that in mind, if we know that we are trying to evaluate, what was it, 0 to pi on 4? Yes. If we're trying to evaluate 0 to pi on 4 of the big nasty fraction, we're better off doing it with the equivalent that we had, which we had sec squared. That's not how you spell that at all. Sec squared x minus 1. So when we're getting our antidiff, then we look at the diff side of that formula sheet. Sec squared goes to tan. The coefficient a is effectively irrelevant here because there's no coefficient of a. It's implied as 1. So that's going to flip to tan x, and the antidiff of 1 is just x. You can put your plus c here if you like, though we are doing a definite integral. So that's the first time I've shown that. I'll just pause there for a sec if it makes enough sense that I've just used the left-hand side, the diff table, to infer what the anti-diff should be, even though they have kind of just crossed it out on the right-hand side. Is it clear enough, the inference that was made there?
Wait, is it sec x as in, is that short for secant of x?
Yeah, so the full wording of that is secant. You got two others as well that are special related. You've got cosec and cotangent. That's the CSC and the cot there.
So the secant of x is equal to the reciprocal of cos x.
Yes. Secant is the reciprocal cos.
Okay.
Yeah, let's prove that by killing these squares, and you can still see it'll show up as true. Yeah, so secant is the reciprocal cos, cosec is the reciprocal sine, and cotangent is, I think it's the reciprocal of tan.
So we won't really need cosec or
No,
cotangent.
I've never seen them be used in methods. I only secant just because of how its diff relates to tan. Otherwise, yeah.
Okay, that makes sense.
Yeah, no worries. Okay, cool. So hopefully the logic there makes enough sense. The rest of this is now just evaluating via our circular function unit circle. So we're doing capital F of pi on 4 minus capital F 0. That's going to give us tan pi on 4 is just 1, minus x, so minus pi on 4. And yep, that's that. Capital F 0, tan of 0 is just 0 because there's no gradient, and minus 0 is 0. So just final answer 1 minus pi on 4, or 4 minus pi or on 4, should you wish to put those all on the same denominator. Yeah, that's about it. That's the end of the chapter review extended response section for integration. Anything in there that needed further clarification? If not, we'll go to the tech-free section.
Chris, I just had a quick question. After today's session, or I guess Friday session as well, are we just going to start prob from next week?
Yeah, probability, probably Friday, unless people have questions about this sort of stuff. Because I think by now, by the end of this week, everyone will have done their calculus sack. If people still haven't done it, like, let me know, and we'll spend Friday. Well, I guess it's too late by Friday because that's the end of the week. But if there is one for people still the next week, then we'll keep doing this stuff. Otherwise, yeah. So message me directly. Tomorrow. Yeah, yours is tomorrow. I understand. That's fine. Yeah, we're definitely doing this. Oh, yours is in a month. Okay, cool. So we'll definitely still keep touching on that. Maybe tell you what, we'll use the Fridays for this sort of stuff as of next week. This Friday we'll look at probability, and then basically we'll touch on probability this Friday. Then as of next week it'll be back to Monday doing unit 1 and 2, Tuesday doing unit 3, 4 probability, and Friday we'll do SAC prep for integration. I think that's how we'll do it. Yeah, no worries. Cool. Okay, what's good in... Let's see if there's a good multi, actually. Maybe not. Actually, this could be alright. This is the kind of question that shows up quite a bit, which is basically you'll be given a set of bound area in a multi-choice, and it'll be like, cool, which of these gives the bound area, the total enclosed area between the two curves? So it's decently harder than if you had to create your own bound area equation, because creating your own means you can just do whatever the hell you wanted. Whereas with this, you have to evaluate each of these on their own merit and say, hey, does this actually get me the bound area? Because, as we should be familiar with, there are multiple ways of writing the same thing for this sort of thing. For instance, one thing to keep track of will be if there are any inverted terminals, right? Like if you go from 0 to 3 rather than 3 to 0, you now flip your positive area to being a negative area. And so you might see stuff like that. You might also see symmetries show up, like in the case of, yeah, even something like this, right? The area on top is the same as the area on bottom. So rather than doing both two separate integrals, they might condense that down into one and then double it. So these are the kinds of things you now need to keep track of. So we have our sequence there. First up would be 0 to 6 of f take g. Is that a good one, or is it a bad one? What's wrong with it, if so? F would be the blue line, G would be the red line. What are we thinking, good or bad? We're trying to achieve the bound area. Typically, the way you would do a bound area equation when it's multiple curves is you identify the durations over which one's on top and which one's on bottom. And then you would do a definite integral of top take bottom over each of those durations, so long as one is on top for the full duration. So the issue with doing 0 to 6 is that you're starting at the origin, going all the way to the end of the bound area, but you're not accounting for the fact that f is not on top the entire time. F is only on top from 0 to 3. From 3 to 6, you now have g on top. So there should be, if you're doing it that way, a split between two functions. There is not a split here. This is not a correct answer. This is what that split should look like. 0 to 3, f take g, exact same function set, but now it's only over the valid domain. We've also got to look at the second bit, making sure that's relevant. 3 to 6, cool, that does in fact get us the second bit, and they've made it g take f, g being the red, f being the blue. The red is above the blue, so we're doing it in the correct order once again. So that would give us the answer B for this one here. Just for the fun of it, the other questions, so 0 to 4 is just a pretty wanky, sorry, that's the wrong word for that, a wonky looking integral. Perhaps the mistake there would be setting the y value on your integral rather than the x value, and also not accounting for the fact that you've got a flip between them. From here, again, it looks like the same sort of problem, using the y values on the coordinates, 0 to 2, and 2 to 4. But this time they have accounted for, wait, never mind, they didn't account for the flip here. They account for the flip here instead. So all these had the problem of using y values on their terminals. These ones used x values, only this one did not account for the flip of which one's on top, which one's on bottom. Cool. I think that might be the only one that was worth exploring mostly. Maybe this actually. Yeah, this one. Okay. So we have two related integrals. We got a known one here, a known one here, an unknown one here. The problem with this kind of question is we don't know what f of x is, and so we can't just chuck this last one into the equation, into the CAS rather. Oh yeah, specific question? Yeah, let's go for it. I'll just finish.
I just need a sec to get it.
Yeah, I'll finish this one up and then you send that through. But okay, so how you handle this is you're going to probably start with the stuff that you do have information regarding and then see how that marries up to what you have here. First thing I'm looking for in these questions is, do the terminals line up in a nice way? What I mean by that is, if I were to look at the numbers, like -5, 4, 4, and 11, do they match up quite nicely with the one that I'm trying to do here? And the answer is yes, they do. From a minimum of -5 to a maximum of 11, there are no breaks between these terminals. And so a likely way of solving this is to identify that this can be nicely split between these two integrals. From here, my goal is to now draw a rough representation of what I'm looking at. So I know that -5 is a boundary, I know that 4 is a boundary, and I know that 11 is a boundary. First one, from -5 to 4, is 2. So we're going to have that highlighted as, I guess, just +2, you know, on some number line. From here, the 11 to 4, we're noticing is flipped the other way around. Usually you have the lower number on the bottom and the bigger number on the top. Because it's flipped, and giving +6, to put this on the same diagram that we have the thing in the regular order with, we're going to now flip that order. So we're going to make it back to being 4 to 11, and in doing so, flips that +6 to a -6. Which means we're now going to have a -6 for the remainder of the duration. From here, we're now told to evaluate -5 to 11. This is now just adding these two things together. If you have an area of 2 here and an area of -6 there, adding the two together, getting you -4, is going to give us our final answer. Part C. I have a whole suite of exact questions like this where you use different properties. This one was using the splitting the integral property and the flip property here. There are other things you can use, like taking coefficients out, and there are some really annoying things where you've got dilation factors on either your x is where the issue lies in those. Those are the weirdest ones to work with, and horizontal translations perhaps, but those don't really show up in the textbook.
Sorry, could you re-explain this? Why is it the -6?
Why it's -6? Sure. Because I'm trying to put these on the same diagram, and so putting them on the same diagram means I want to make sure that all my terminals follow the same convention, which is the bottom number should be the smaller than the top number. Right, like I'm drawing this thing left to right in ascending order, and the problem with the second integral was that you have 11 on bottom, 4 on top, whereas if I wanted to represent this properly on my diagram, I should have that from 4 to 11 instead.
Okay.
Yeah. So you're familiar enough with the fact that when integrals flip, the number flips sign?
Yeah.
Yeah, sick. Okay. Cool. Okay, we had the question come through. Let's suss it out. I wonder, so this is a Zoom window that I've opened. I wonder if I can screen share a Zoom. Yeah, no, I can't. Cool. Let me download that as its own separate thing. Okay, and we'll have a look at this. One second. How's that for you guys? Screen share good enough? Let me know.
That's good.
Yeah, sweet. Okay, was there a part of this specifically you wanted to have a look at, or just top to bottom?
Yeah, if we had time just to go through.
Yeah, top to bottom, sure. So we got our function, it is a cubic, and the first question is to find the coordinates of the turning points. How are we going to do that? How do we find turning points of any function? The answer, of course, is to do diff equals 0. So let's exactly go ahead and do that. Solve derivative of function equals 0 for x. That's going to get us the x coordinates that we need, and we're just going to plug those back in to get the equivalent y coordinates. Is this a symmetrical cubic? Looks like it. So I'm going to go ahead and assume this will come out to be plus minus the same y value, and sure enough, it does. So getting the coordinates of the turning points, you'll just, again, marry up those x values with those y values. Next up, so x equals -1 and x equals +1 both exist on the graph. Find the equation of the straight line that connects the two. Cool. We have 2 points. We're trying to find a straight line. How do we use 2 points to find the equation of a straight line? Okay, I'm hoping you guys just want me to run through them rather than not knowing how to do this, because it's a bit of a worry if we don't, but that's fine. I'll run through it. Okay, so I'll do this in the form of the y take y1 equals mx take x1, the gradient point formula. And you can even just sort of do this off rip on the CAS as well and have it evaluated for you. So you would do something like y minus the y1, which I'm going to say is the point A. So that's going to be f of -1. So that's my y1 equals m, the gradient. So we're doing y2 take y1 on x2 take x1. That's going to be h1 minus h minus 1, 1 minus -1. Just making sure I got them in the right order again. So we definitely wanted y2, y1. Yep, cool. That's all consistent. So that's our gradient m, x take x1, so it's going to be -1. And then expanding that all out, you'll get, let's define it. So we'll get 4x, or -4x. That'll be -4 plus another 4, so 0. And I guess that should make sense, right? If we see the symmetrical kind of nature of the cubic, because the points are equidistant from each other, one to the left and one to the right, it kind of makes sense that would cross at the origin. So that's a nice little point of validation. And you could even do a further point of validation by graphing on the CAS, both the original function and this new function, making sure they do in fact go through the points you expect. Yeah. Okay, find the distance AB. So now we're doing distance between points. Does anyone want to suggest a way that we can do distances? I think you came off mute for a second, but maybe you changed your mind, or did it break?
I was questioning it.
Well, part double I, distance. We're now finding the distance between those points.
Distance formula.
Yeah, distance formula. There we go. Cool. Okay, so let's do that. It's just going to be the difference in x value squared plus the... Wait, plus? A squared plus b squared equals c squared. Yes, plus. Plus difference in y values squared. So let's do exactly that. Square root of x2 take x1. So it's going to be 1 minus -1 all squared plus the y values. So now we have h of 1 minus h of -1 all squared. Bang, distance. Okay, new function. Let g be the same sort of thing, but now we've got a k involved in it, and the next set of questions are now the same, effectively. Really nice that we were using like h of x in this whole thing, rather than using the actual values, because it means that when we do our part C, we're effectively just going to copy down exactly what we did for the distance equation last time, so long as we redefine our function properly. So g is now x cubed plus minus kx. Minus k times x. Make sure you put that multiplication symbol in there yourself. The CAS will not do it for you. Yep, points are effectively the same. Find the distance just means we're going to grab this and replace our h's with g's. So even though we did know that h of 1 and h of negative 1 were values, here's the advantage of not using those values. Yeah, works out really nice, doesn't it? Cool. In terms of k, let me just tell you, yeah, definitely still terms of k. Nice. Find the values of k such that the distance is equal to k plus 1. Well, we have our distance. We're told the distance needs to be equal to k plus 1. I want to figure out what values of k achieve that. Anyone want to give me an idea on how we might do that? Reminder that this result that we just achieved was distance. Right. Yeah, so we're doing part double I here. Find the values of k such that the distance is equal to k plus 1. What we solved in the previous question was the distance CD. So this is just saying, hey, take a previous answer, make it equal to k plus 1, and figure out what the values of k would be to achieve that. That's what's being asked here. So we'll do exactly that. Cas solve, grab our answer, make it equal to k plus 1, and then see what happens. We get two possible k values. Let's suss out to see if k had any requirements attached to it. K must be a positive real number, and so both of these are positive real numbers. Yeah, cool. Yeah, both is fine. So, and also there's a plural in the part double I, find the values, plural, so we're pretty happy to use both of those. Yeah, you're right. Part D, diagram shows the graphs of g and the graph of y equals x. So as a reminder, g was that new thing that has k in it, and we're also plotting it across y equals x. Oh, excuse me. These graphs intersect at 0, 0 and a. Yeah, makes sense. If it's intersecting at y equals x, then the x and y coordinates should be identical. It's y equals x. Part I, find the value of a in terms of k. Okay, cool. So whenever it says find something, just at all, I'm looking at where that thing is. So it says find a, effectively. A is the x and the y coordinate of the intersection between g and the graph of y equals x. So I know when it says find the value of a, it's really telling me find that intersection point. The fact that it says in terms of k is almost irrelevant. We know that we're finding an intersection point, and the way that we find intersection points, as always, is make the two equations equal each other. Make g equal x in this case. Menu, sorry, 1, g of x, yeah, I definitely called it g. G equals x, comma, x. We're specifically going to say x because we're trying to solve for an x coordinate. Don't do comma k, even though you want to have k in it. K is already going to be in it regardless. That's going to give us a few things to sort of digest. Whenever I get this domain related shit, I kind of just go back and see if me putting in my own domain fixes it. So for instance, if I say given that x is greater than 0, maybe it'll fix it. It does not in this case. Maybe I could also put k is positive. So if I put a space in here and literally write the word and, A-N-D, another space, k greater than 0, maybe that'll further knock off all that stuff. Yay, look at that, we did it. So the only one that matters there is going to be the root k plus 1. So yeah, for those who didn't know, you can put multiple conditions on your domain here, as long as you separate it with the keyword and. And the space bar is basically right next to the Z on your CAS. Otherwise, you don't really need to do that. You know, if you look at this stuff enough, you start to realize that it's like, okay, cool. The gist of what's happening is it's telling me that you've got the plus minus roots as your answer. And so you might just look at your scenario that you've got written out on the paper and be like, okay, well, the negative root's not going to happen because they're both positive numbers. So we just take the positive root instead. So to get a in terms of k, if we remember that a is an x coordinate, well, we've achieved it. Instead of saying x is that, we say a is that. And lastly, for the last minute that we have, find the area of the shaded region in terms of k. This is once again a top take bottom. Y equals x is on the top, g is on the bottom, and we know where we are doing our terminals from. We're doing it from 0 to k plus 1, or rather the root of k plus 1. We're doing y equals x on top and g of x on bottom. And that's going to get us our bound area in terms of k. Perfectly timed with the end of the lesson. Imagine that, finishing on time. Alright, I'm happy to stick around for a little bit, should we need to clarify anything further about that. Otherwise, for the most part, these should have been more or less decently straightforward things. You know, finding distances, finding areas. Maybe it gets a bit weird when you've got sliders like k, additional variables. So hopefully this demystifies what you do with that sort of stuff. If there's anything else you guys need from me, let me know. Otherwise, thanks for coming. And
Thank you so much.
Friday we'll do our probability. Thanks, guys.
Thank you.
Thank you.
Cheers. Yo.
Thanks, Chris.
Yeah, no worries.
I just want to say, I guess this is some stuff. I've got my prob stack on the 3rd of September.
3rd of what?
September.
September. You've got a bit of a muffle going on. Yeah, okay. Do I have your planner?
Wait, can you hear me now?
Yeah, that's way better.
Okay, I said 3rd of September.
3rd of September, okay. Do I have your planner?
I can give it to you again.
Oh, no, if you sent it before, then surely I've got it. Oh, wait, no, because your planners come in, like, sections. I don't think you get the full year in one go, did you?
No, we do.
You
I'll
do?
send it
Yeah,
right
yeah, definitely send that, because that'll make it a lot easier. I think last time I only saw the first part of it. Or maybe you've only screen shared it, one of the two.
now.
But
Yeah,
yes.
the dates aren't like super accurate.
Yeah, that's fine. Just need as long as the order is fine. Yes, there's more pages. Okay, maybe I was just too dumb to scroll down. Cool. Alright, well that helps definitely. The dates of the tests aren't accurate, or?
Sorry? Or as in like where it says the stacks are.
Yeah, is that fine?
Oh, they're like inaccurate by like 3 to 4 days.
Okay, yeah, days, as long as it's not like 1 or 2 weeks more, then we're doing
Yeah.
alright. Yeah, no, fair enough.
But yeah, it's pretty crazy because I have like for all my subjects, the last SAC, and then like trial exams are literally like you don't even have time to study for trial exams. It's just like you do the last SAC and it's like, yep, here's a trial exam for the whole year.
Yeah, it's pretty fast paced. But
Yeah,
we'll,
honestly, it doesn't really.
yeah.
Yeah, trial exams don't really matter that much unless you're going for like the docs of the year level.
Sure, yeah. I mean, it's there to... Yeah, it's not going to have a major impact on more or less anything, other than your confidence, I guess,
Yeah.
which is a tangible thing.
How manageable is the workload for prob? Like, do you think I can just concurrently like review everything else?
Prob's pretty chill, I say. Discrete and binomial is stuff that you guys... Well, discrete specifically is stuff that you probably would have learnt in like earlier years of probability.
Yep.
Binomial just touches on that a bit more. Continuous is basically just doing integration all over again. So all you got to do is flip your mind into saying area means probability, and that's it. You have all the skills you need already.
Yep.
Normal distribution, you're making use of CAS functions almost exclusively. And
So is there a lot of overlap between calc and prob?
yeah, so calc and prob continuous probability, 100%. Normal distribution section, like 50%.
Yeah.
That's
Do you have
about
any
it.
advice for like approaching prob or like what I should be doing in between our sessions?
I mean, for now,
From tomorrow, I'm basically.
yeah, tomorrow you're doing it, so there's not much point me saying just focus on integration right now. Obviously, right now, focus on integration, but as of afterwards, you know, you've got access to the whole suite of lecture stuff that we've got here. Even just doing the questions ahead of time yourself, see how you go, right? See if you can sort of speed run some of the earlier stuff yourself. The main way of going about getting the most out of this sort of thing would be doing as many questions as you can ahead of time, and where you're starting to stumble, you bring those to me in the class, and then we look at those.
Yeah.
That's like the fastest way of going about things.
Yeah, I feel like I'll probably try to learn the concepts before class. 'Cause I feel like it's
Yeah.
because when I've been learning them in class, it's like cutting a bit tight.
Yeah, it always pays because like if you have a look at the curriculum content stuff, like listening to those videos ahead of time, even if you don't do any of the actual work, just seeing the concepts and seeing that you've
Oh, you're
Yeah.
talking about the summary videos you have, right?
the videos and the
Finish
lecture
it,
documents. Yeah.
Yeah.
If you have a browse of those, even like 2x speed or whatever, just to get the concepts in your head, at least when you then look at it in class for the second time, it is the second time you're looking at it, not the first.
Yeah, okay, that's probably a good idea.
Yeah, so they're all there to help you either get ahead
Yeah,
or study.
Do you have the document where it's like what things we cover in what class? Like, are we sticking to that right now? Or...
Oh yeah, the curriculum kind of needs another refresh again. We spent a lot of time on the calculus review stuff because I kind of make these to try and match what people are doing, and then I realize that I'm trying to serve two things at the same time. So it's gone through a few revisions. I guess because I guess we can
Oh yeah, that's fine. I
update
think,
those
but
now.
you'll probably go through the topics in the same order.
Oh yeah, the order absolutely. Yeah, like now especially.
Yeah, I just needed the order, honestly. I wasn't really too concerned about the timing.
Yeah, I mean, my thing was just that I just didn't actually really know when people would have their sacks, and so I've got so many weeks ahead of just like, oh yeah, you could learn all the probability before you've even touched the integration sack. So we're still definitely going to do it in the same order, and it's the order of the textbook.
And
but
then
yeah.
after prob is just exam revision.
Yeah, 100%. Well, we'll do prob revision up until the prob sack, because I think that's still one of the better ways of going about it. Get all the... Don't worry about your previous stuff until you've done your probability sack. But yeah, after probability sack, then yes, we'll grind out a bunch of practice exams for classes 2 and 3, because Unit 1 and 2 will be a bit slower. You guys are going to have the exams early November.
Yeah, and that'll be good because we're all doing the same... Well, getting ready for the same thing at the same time.
Yeah. I mean, Unit 3-4 pretty much is that across the board for a lot of schools.
Yeah, and I think it's like a lot more weighting on the exams, like 60%. Basically.
Yeah, not only is it weighted higher, but it also scales your other marks as well.
Yeah.
Because, like basically, if you did really poor on the exam but really good in your sacks, not only do you lose that 60%, but your other stuff also scales down. So not great. Definitely don't screw up the exam. No pressure or anything, but you'll have plenty of time to practice it. You can see how far ahead of a schedule we get when we go through this sort of stuff. So, geez, I can't even count the number of weeks we've been doing specifically integration prep. It's crazy.
Yeah, I'm honestly can't wait to.
Exactly.
I don't even care how it goes.
Just get it over and done with. My God, stop talking about bloody integrals.
Actually looking forward to prob. I feel like it'll be pretty good.
Probably chill. It'll be one of those things where it's hard at the beginning but then easy at the end, because all the questions are scenarios. They're all extended response. And extended response is hard. But if you do a lot of them, it gets good. So there's only a certain threshold of how bad these can actually be. And unfortunately, the case is that you get them at the start. But once you cross over that threshold, you're now happy.
Yeah.
It was my highest marks in when I did methods. I got a near perfect score on probability. Failed 1 mark on the SAC, tied highest.
How do you reckon you'd go if you did VC methods now?
If I did VC methods now, I mean, I'd obviously mulch it. It would be. I mean, we did it. Actually, no, you weren't here last year. Yeah, you weren't here last year. I don't think so. Yeah, we when I was doing through the practice exam series, one of my students asked, "Hey, in one of these lessons, can you just do a past exam and do it end to end, and maybe just like talk through what you're doing?" And that's what we did. We did it at Tech 3. And that was with me narrating it. I think I missed like one question on the exam. So with me narrating it to the class, we got a decent amount of the way through it.
Oh wow, that's actually pretty impressive.
Yeah, no, it's the advantage of doing one subject for 3 years as an adult. So it's not hard to do, but I guess it proves that, when you're just doing this day in, day out, you will be good at it. So it's a matter of reps.
Yeah, sounds good. Awesome.
Anyway, we'll be there to
Great.
support. Thank you.
See you on Friday.
See you then.